In our previous example, we saw that the decision boundary was linear. So we predicted that if our hypothesis was less than 0.5, we would make the prediction that the student would not be able to get admitted to the university. And if our hypothesis was more than 0.5, then the student would be admitted to the university. But there can be cases when the decision boundary is not going to be linear because the distribution is not going to be partitioned in a manner where a linear decision boundary would be able to make the prediction. In this case, we would need something called a regularized logistic regression. The regularization is an important factor because it helps to make a decision boundary which contours to the data set. So we have a new exercise where we are asked to see whether a microchip is going to be accepted or whether it is going to be rejected. So the distribution of the data set is visualized in this graph. So for those test results that have the pluses, the squares as the output, those are the only ones that have been accepted, and the yellow circles have been rejected. If we were to draw a straight line boundary decision anywhere, it would not be able to accurately predict whether a new microchip would be accepted or predicted. So this is the challenge that we have for this part of the exercise. So let's see how we solved this problem. First, we are asked to visualize the data. In order to visualize the data, the plot data function that we had, that is going to suffice. So let's see how the regularized code has been written. Okay, so just like before, we have loaded the data. We have our X for our tests and Y for our output, and then we have plotted the data for X and Y. The plot data function we already completed for our last part of the assignment. Now, the difference is going to be in the theta vector that we have. So we notice that there is something called map feature. We need to understand what map feature is. So let's check that out. So what essentially map feature is doing is it is creating a vector theta so that we have thetas as coefficients for x1 and x2 up to higher degrees. Concretely, we can visualize this where a map feature of x is going to output x1 and x2, the square of x1, the square of x2, the product of x1 and x2, all the way up until we have till the 6th degree. Okay, so how does that help? Essentially what we're doing is we're adding more features. If we go back to the previous part of the assignment, we only had exam 1 and exam 2, which were x1 and x2. We did not raise these to a higher power. Now, raising these to a higher power introduces new features which may give us a better prediction. Now, Andrew suggested we go up to the 6th degree. It could be so that having so many degrees could be detrimental to our prediction, which is why we need to regularize it so that the thetas that we have, they can regulate how much each of these will impact our prediction, how much each of these x's are going to impact our prediction. So what are we asked to do? We're given the instruction first that due to having map feature, our theta becomes a vector with 28 dimensions. We could possibly not visualize 28 dimensions. So we have further written here, logistic regression classifier trained on this higher dimension feature vector will have a more complex decision boundary and will appear non-linear when drawn in our two-dimensional plot. So this is what we want. This is our target. So while the feature mapping allows us to build a more expressive classifier, it also more susceptible to overfitting. Well, we are familiar with the concept of overfitting, which essentially means that the decision boundary that we have, instead of going as a smooth contour of the edge cases, we would most likely get a decision boundary that wraps around, that does a lot of work to wrap around all the data sets. So it might fit the training set really well, but we would be compromising on making predictions. The decision boundary would be so twisted and convoluted that we would not be able to make a prediction for, say, a chip that should have been rejected. We could essentially have that being passed through the decision boundary, or a chip that should have been accepted might have gotten rejected. So in order to do these, we have to adjust the cost function and the gradient. So we have added a regularization term at the end of our cost function and a regularization term at the end of our gradient function. What we effectively have is the same cost function that we had before, but now we square the theta jth term and we multiply that with lambda by 2m. Now, if you remember, lambda is basically what controls the how much we're going to penalize theta for being too high or too low. Essentially, if it is too high, then we would be updating the cost function in such a manner that our the next iteration of theta would heavily be reduced. We try different values of lambda, and that affects how the decision boundary is going to turn out. But we will look at that later. What is important right now is to understand that the cost function is altered. So we need to implement this for our regularization part of the problem. And for the gradient, we need to implement this in order to regularize the gradient. Now let's see how we have been able to do that. We have a cost function regularization called cost function reg.m. Now we are getting back the cost and the gradient. What we input is theta, x, y, and lambda. Lambda is a term that has been introduced. Now we're using lambda basically to regularize our cost function. Okay, so we are given the length of y, stored that in m. This helps us get the dimension of how many training examples we have. We set the cost to be 0 at first, and then we set the gradient to be 0. Now, since the gradient depends on theta, the size of the gradient vector is going to be the same size as the theta vector. Now, simply speaking, all we have to do is use the hypothesis like we did before, have the same cost function like we did before, and then add this term. An important thing to notice here is that if there are 28 features, n is 28, we cannot take j equals to 0. So that's why this term begins from j equals to 1. So when we make the summation, we need to account for the fact that j equals to 0 is not added as the regularization term. How have we done that? Well, we introduced a term called cost reg term, that is lambda over 2m, which is this part, multiplied by theta squared. Now I went for theta transposed times theta. This is going to give me theta squared, but theta 1 or theta 0, in the way we write it and the way Octave reads it, theta 1 in Octave corresponds to theta 0 in the way we would write it. So we need to subtract that part. Now notice that lambda by 2m is multiplied with the summation. So the summation part of that is this entire thing here. Let me resize this so I can better demonstrate to myself. Okay, so theta squared minus the first theta term. So this theta 1 corresponds to theta 0 over here. So now that we have the regularization term for cost, we simply need to add this to the previous cost function that we had. So this highlighted part is the previous cost function that we had from before. Just to show you, here is our previous cost function. They are essentially the same. Okay, and then we just added the cost reg term, and that essentially gives us the correct cost. Now similarly for the gradient, we need to add the regularization term, but we need to make sure that theta 0 does not show up in the regularization. So to achieve that, first let's count how many thetas we have using n equals size theta. We stored that in variable n, and then we have a gradient reg term, which is lambda by m multiplied by 0 times theta to n. Now what does this mean? So if you observe this part, you have the vector theta, but you take the second element up until the last element. So whatever the first element, well, that is 0. The reason I chose to have it as 0 is because we are adding the term, and adding 0 to this expression is going to keep this unchanged. So effectively, we are going to add this regularization term from j is equal to 1. Again, to remind yourself, j is equal to 1 corresponds to, theta j, where j is greater than equals to 1 corresponds to theta 2, all the way up until the last term. So the gradient function is still unchanged. We simply took that from the gradient function that we had before, rather the gradient expression that we had before, and then we just added the gradient regularization term. So doing this lets us get the correct answers. So I'll go Ex2 reg. I'll show you that this is done correctly. So our plot data function worked correctly. Actually, let me clear everything so it is easier to see. Here we go. So our data set is represented correctly. So what do we see here? Oh, there's a warning. Colon arguments should be scalars. Warning call from cost function at column 25. Oh, we'll deal with that later. It's just a n is equal to 28.1 for some reason. That's fine. Okay, so now what do we have? We have the cost at initial theta. This is when the theta were all zeros, so our cost matches. Now, and the gradient at initial theta, we check the first 5 values only and they match as well. Okay, fantastic. Let us move on. Okay, so we get the warning again. I think I'll address this after the video, but I don't think we have to worry about it for now. It's just I guess this is my first bug in my programming. Okay, so now we try with lambda 10. and we get a expected cost of 3.16, which matches here. Then we test our gradients when lambda is equal to 10, and we see that the gradients match. Okay, so essentially that has worked well. And if we plot the decision boundary, we get what we expect. And our training accuracy is 83.05. We're expected to get approximately 83.1, so we're good there. Now, one thing I want to show here again is, if you notice the edge cases, a lot of microchips that did pass, or a lot of microchips that did not pass, they do go over the decision boundary, which is why we're getting a training accuracy of 83. So now the question is, how did we get this decision boundary? So to be frank, this decision boundary, I'm not entirely sure. I'll go through it and see how much I can make of it. But most likely this one is going to need a few more revisions in order to understand. So we are the else case from our previous video. First, we set the axes. We have set the axis from -1 to 1.5 with 50 points. What this is doing is, we're starting from -1, we're going to 1.5, and in between these we are going to have 50 numbers. So same thing we do for v, and v here corresponds to the other axes. All right, now we have set a vector z with all zeros, with the number of rows corresponding to u and the number of columns corresponding to v. So this is a square matrix. Now we want to compute theta transpose x. If we compute theta transpose x, effectively what we're gonna do is find the equation for the decision boundary. That's what I understand from here. Like, similarly, we did something like that for here. I mean, we set theta transpose x equals to 0, and we found that, right? So that would be my guess. So theta transpose x is, here he wrote theta x, but if you notice here, he did theta transpose x. So he used map feature. He called that function again, and he had uivj, so he's corresponding to the ith u and jth v, and multiplying that element with theta to get a value for the ith and jth element, for the ijth element of z, right? So now we have a vector z with the feature mapped onto theta x. Okay, then we have to transpose it, and then we contour the plot. I don't understand what plot z equals to 0 means here. Effectively what we're having is, I think, x, y, and z. That may be the contour plot. Actually, while we're here, let's type help contour, see what we get. Okay, so what is that doing? Contour is a function. Okay, so the format is contour z, zvn, xyz, xyzvn. What format do we have here? We have xyz, and we have a vector. I think that is vn, and then we have the style, right? Okay, so what does vn do? So that's not written here. Okay, and ch creates a 2D contour plot, right? Okay, so ch equals contour. Do we have ch equals contour? No, we don't. Okay, so the appearance of contour lines can be defined with a line style as the same as plot. Okay, that's just the first argument. Hix is an axis handle. Okay, handle for axes. then plot into this axis rather than the current axis written by GCA. What is GCA? I'm not sure what GCA is. There's an optional output C, contains the control levels in control C format. So, okay, let's look at this example. X is from 0 to 3, Y is from 0 to 2, and Z is Y transpose of X. So, contour X, Y, Z, 2, 3. Okay, let's run this, see what happens. Okay, do we have it? Oh no, that's going to be a very big list. Oopsie. All right, we are back. I sort of bricked it by hitting Control V. Where are we? Oh no, we don't want to be here. We want to go to X2 Octave. Okay, are we in the right folder? Yeah, we are. So let's run X2 Reg one more time. Oh no, we were looking at contour help contour. Okay, so let's type X goes from 0 to 3. Y goes from 0 to 2. Z goes from Y transposed multiplied by X. And then we contour X, Y, Z, 2 to 3. What does this give us? It's not really that helpful, is it? Anyways, let's go back to our example. Right? And we hit enter. We hit enter again. So we are back with it. Let's look at plot decision boundary. See what we're doing. So Z has been transposed. I think this thing here we should spend more time understanding it, not on the video. Okay, so effectively that has made our prediction successful. We did not necessarily have to predict whether a new microchip is going to get accepted or not. There is an optional exercise which I'm not going to go over, but hopefully this is good for your reference in the future, and then we'll move on to week 4, and when the time comes I'll start uploading the assignments. All right, good luck and see you next time.